So the last one was a bit of a doozy, and by doozy I mean it was 18 minutes long, and that will not happen today. One of the reasons for that is because we're actually eliminating a portion of the double replacement reaction, something that you have to take into consideration. With single replacement reactions, you have to worry about the solubility. That determines whether or not the reaction proceeds. There is something that does the same thing for double replacement reactions. It's not the activity series, it's something else, but we are again going to worry about that later. So right now we're just going to worry about predicting the products. So when you have a double replacement reaction, you recognize it by its reactants because you have two ionic compounds that are reacting to form two different ionic compounds. So the easiest way to make this happen is just to switch the cations in each compound. So remember, the cation is the one that comes first. It's usually the metal, unless it's ammonium. It's the positively charged ion. So in this case, it would be A and C. And notice that these two switch partners. Okay, so whereas A was bonded to B, now it's bonded to D, which was C's partner. I don't know if they made you guys do swing dancing in middle school PE. They made us. It was not my favorite. 7th grade boys are very sweaty. But that's forever my analogy for double replacement reactions. It's like swing dancing. You're just switching partners. Okay. So I'll show you multiple examples. What's really nice about double replacement reactions is that polyatomic ions are going to remain intact. As opposed to, remember with decomposition reactions, when we did ternary reactants, those polyatomic ions would decompose into other products. That does not happen here since the ions are just switching places, so we don't have to worry about that. Now, I alluded to this at the beginning, but just so you know, double replacement reactions don't always happen, just like single replacements. Double replacements only proceed if at least one product is a solid, a liquid, or a gas. Now you might be looking at that and go, okay, well that's all of them. Well, there's one that we're leaving out, and that is aqueous. So if both products are aqueous, remember aqueous means dissolved in water. Something's dissolved in water, that means it's ionized. If I have two compounds that are fully ionized, that just means I have 4 ions floating around. Nothing forms. Nothing happens. Okay? So in order for something to quote-unquote happen, in order for there to be a chemical change, I need to form something new that is a solid that's going to form out of solution, a liquid that will separate, or a gas that will bubble out. If my two products are both aqueous, then nothing changed. What we will go over next week is how to determine if the ionic compounds are solid or if they dissolve in water and form aqueous compounds. For now, remember, we are just assuming that aqueous or that ionic compounds are aqueous in water. A lot of them are, and again, we'll come back to that later. Right now, we're just going to focus on the mechanics of how the double replacement actually happens. So, for instance, let's say that we have these two solutions. We've got a silver nitrate solution and a sodium sulfate solution. Okay, and I pour them into one beaker. So I've got silver nitrate dissolved in water, sodium sulfate dissolved in water, and I pour them into the same beaker. I'm going to leave off phases for now because, again, we'll get to that later. What we're going to focus on is the double replacement. So our two cations are sodium and silver, and remember, they're going to switch places. In other words, they're going to switch partners. So whereas silver was bonded to the nitrate, it now wants to bond with the sulfate. So silver is always a 1+, sulfate's a 2-. I'm going to make Ag2SO4, and then the sodium will bond with the nitrate and make NaNO3. And the last thing we have to worry about for our purposes this week is just balancing. So I'm going to double my amount of sodium, or rather silver nitrate, and the amount of sodium nitrate produced. And that covers it. That's literally it. So let's do a couple more, and then we'll worry about solubility later. So let's say we've got a solution of calcium hydroxide. It's going to react with the aluminum chloride. So another solution. If it helps, you can color code these things. You know how I feel about colors. Okay. So cations are going to switch places. Aluminum and calcium are going to switch partners. Remember, aluminum and calcium are not going to bond with each other. That's two metals. They're going to form two positive ions. That doesn't make sense. Cation needs to bond with an anion. So calcium, it's kind of like foiling, honestly. Calcium is going to bond with the chlorine, and then aluminum is going to bond with the hydroxide. Remember, the cation always comes first in the compound. So we're going to make calcium chloride, that's CaCl2, and then aluminum hydroxide, which is AlOH3. Alright, to balance this, let's see, I'm going to have to triple that, double that, which means I need 2 of those and 3 of those. That's it. Alright, let's do one more. So this time we're going to take a solution of lithium phosphate, so Li3 PO4, and let's react it with magnesium oxide. Okay, cations switch places, lithium and the magnesium. Oh, the reason I color coded, let's go back to that, sorry. So here's my chlorine and my aluminum, so notice that my 2 blue guys are now separated and my 2 pink guys are now separated. Okay, so if that visual helps you, go for it. If it doesn't, then don't worry about it. Again, apologize for missing that. So the lithium is going to bond with the oxide, we'll make Li2O, and the magnesium will bond with the phosphate, we'll make Mg3 PO4 2. Alright, and to balance this, remember minnow, metals first, so we've got 3 magnesiums, put a 3 right there. It's going to triple to the amount of oxygen, so I'll put a 3 right there, which gives me 6 lithiums. I'll double my lithium phosphate, which gives me 2 phosphates, which I already have. So that's done. Alright, so that's the mechanics of double replacement reactions. We'll worry about solubility, which will determine whether or not these reactions happen later. And again, the only requirement is that one of your 2 products is not aqueous. If they are both aqueous, then there's no reaction.